All right, so today, basically what we're going to be doing is we're going to be going over two different ways to integrate. And the first method is trigonometric integration, and then the second method is trigonometric substitution. So attached here are two charts or formula sheets from class that'll help you. The first one is with trigonometric integration, and the second one is with trigonometric substitution. They're different types of problem. So what you'll notice is that for these problems, they're actually going to be composed of sines and cosines and secants and all that. But the ones over here are just going to be regular numbers, in a radical. But the difference is that we actually convert these numbers into trig functions to make it easier to solve, because there isn't an explicit rule that'll tell us how to integrate this. So we have to kind of work around that. But the first few problems we're going to be doing are going to be involving these rules. And if you know these rules, or if you just, it's basically kind of steps you should follow. If it's if this is one thing, then follow this path. If this is another thing, then follow this path. And it's basically telling you what to do if a problem looks a certain way. So let me go to the review and actually show the first problem, which is going to be the trigonometric integration. So let me share it with you guys. Okay, so, and make sure to have that chart in front of you, at least while we practice these problems, because it's really going to help. So it says, evaluate the integral of sine to the fifth of t dt. So we're going to be using the first little chart, and I'll tell you when we get to the second one. But the first thing you have to look at is the exponent, and that's really the most important part, at least when you're dealing with sines and cosines. When you're doing these types of problems, this is what will come in pairs. Sine and cosine will come in pairs. You'll notice that secant and tangent will come in pairs, and then cosecant and cotangent will come in pairs. Just keep that in mind. Okay, but for this particular problem, it says the integral of sine to the fifth of t dt. So the first rule that I noticed that goes with this is actually rule number one. It says if the sine is odd, if the power of sine is odd, save one sine and then convert the rest to cosines. So that's exactly what we're going to do. So since this is odd, we're going to save one sine, and I'm going to actually break it up a little bit. So I'm going to save one sine and then leave the rest of the sines on the other side, because we're going to convert this section over here to cosines. But let's get there first. So I saved one sine. Now I'm going to convert this to cosines. But how do we do that? Well, there's the identity, and you're going to have to know these identities. And I'm going to go with the first one first. So the first identity that I think it's important to know is that sine squared of x plus cosine squared of x is equal to 1. And this helps us because we know that sine squared of x, remember we're dealing with sines here, is equal to 1 minus cosine squared of x. So essentially, remember, we're looking for sine to the fourth. If you square this, you're left with sine to the fourth of x. We know that that's equal to 1 minus cosine squared of x, all squared. And that's kind of how we manipulate an identity to fix our problem, because notice how it says save one sine, convert the rest to cosine. So we need to convert the rest, which is what I'm boxing in green, to cosines, which is right over here, because using the identity, that's what we know it's equal to. So I'm just going to plug this in over here. We know that sine to the fourth of x, or in this case of t, is equal to 1 minus cosine squared of t squared, and then dt. So does that make sense so far?
Yeah, it does.
Yeah.
Okay. So I'm going to erase everything over here. But now what we're going to be doing is kind of just expanding and then integrating. And the reason why we can do this, and the reason why these rules even exist, I'll give you guys like a little preview, is because when you expand this all out, you're eventually going to get something like cosine t squared, and then you're going to have like a sign on the outside. Well, remember the rule when you're dealing with the power rule for integration. If the derivative of what's in parentheses, or whatever, if your derivative of the inside is on the outside, then you can integrate. And at least for this particular problem, the derivative of cosine of t is just negative sine of t. So all we would have to do is just add a negative there. And it's really, really easy to integrate with the power rule. And that's the whole point of this. To integrate using the easiest integration rule, I would say, which is if the derivative of the inside is on the outside, you're good to go. So let's get there first. So the first thing I would do is expand this over here. And just to expand that, here, let me do this in another color. Sine of t, this expanded is 1, 2 cosine squared of t plus cosine to the 4th of t dt. The next thing I would do is, well, the next thing you have to do is now distribute the sign to each single term. So when you do that, you get sine of t, you get negative 2 cosine squared of t sine of t. That's a plus. And then you have cosine to the 4th of t sine of t. So now each single term has a sign because we distributed it. I'm gonna erase the top so that there's more space to work. And then I'll show you what to do. Now is the point where I would split things into separate integrals, because you're gonna have to use like a slightly different rule for each term. So this one will be a different rule, this one will be a different rule, this one will be a different rule. And at least for math, when I'm working things out, I think it's easier to split it up like that, because you know, when you're splitting up the integrals, you kind of want to know which rule you're applying to which integral. So remember that when you have something as big as this, you can split it up by writing it like sine of t. And remember to add a dt whenever you split the integral. Minus, I would move the 2 to the front as a coefficient. The integral of cosine, let me erase that so it's clear. Cosine of t squared sine of t. And the reason why I already changed that slightly is because remember the rule. The derivative of the inside, if it's on the outside, we're good to go. So I'm making it into a different form so that we can kind of test for that rule. dt, can't forget that. And then the last integral, cosine of t to the 4th, sine of t on the outside, dt. And now we're kind of ready to integrate each one by one. So the first term is actually really easy because it's just a formula that is very common and we should already know. The integral of sine of t dt is simply negative cosine of t. So we're good to go there. Now we're going to go with this term. So when we're looking at this integral, we have to see if the derivative of the inside is on the outside. It's almost there. We just need to add a negative. We just did wait, never mind. We just I already went over this, but the derivative of cosine of t is really negative sine of t. So it's really just missing a negative. But remember, what we do to the inside, we also have to cancel out on the outside, because we can't just add numbers and manipulate things whatever way we want. So we added a negative there, so we're making this a positive, which is really, we're making this a double negative, which is a positive. So I just make that a plus sign. So now we can use the power rule, because we see that the derivative of the inside is on the outside. So remember, the power rule is just you add an exponent and then divide by the new number of the exponent. So this becomes cosine of t to the 3rd. We raise the exponent by 1, and then we divide by that new number, which is dividing by 3. Last term. Let me not write a plus. same thing. It's the same cosine and sine. We just need to add a negative here and then make this a negative, because when you have a plus and we're making a negative, it just becomes negative. So now, now all we have to do is do the same thing. So we raise the exponent by 1. I'm going to move the negative here. So I'm going to raise the exponent by 1, cosine of t to the 5th, and then divide by that number. So, and then of course, never forget plus c when you have an indefinite integral. So now all we have to do is kind of just, that answer is actually perfectly fine, but I'll tell you guys how she wrote it. When you're converting these back, it's definitely prettier if you write it like this. So the way I wrote it, the final answer was negative cosine of t plus 2/3 cosine cubed of t. We move the exponent to the outside for the integration purposes, but remember that when you have an exponent for any trigonometric function, it's supposed to go like in that little spot between the letter and the function. So I moved it back there. And then the last term is negative 1/5 cosine of t to the 5th plus c. And that's the answer to this problem. Did that make sense? Or
yeah, it actually made sense once I knew like what formulas to follow.
okay, perfect. So I want to be able to get done like a lot of different problems. So the review itself, you can do it on your own, but a lot of them are like the same. So I'm gonna skip just a few just so we can actually get quite a few done. So the second one over here is very similar to the one we had just done. Now we're just gonna be following the rules for cosines. So it's the same process, I would say. And now that you know how to manipulate sines and cosines, I think we can go to a different one. And I want to do this one. So follow the rules for cosines for this problem. And it's rule number 4, where the cosine is even. So just keep that in mind. So let's do number 3. Actually, wait, let me see. Okay, let's do number 3. So number 3, again, is another rule, and it actually kind of goes into number 2. So I'll do this one instead. But now we're just gonna be using another rule, essentially. So let's see. It says the integral of sine of 2x to the 4th dx. So the first thing that I notice, and the first thing you should always pick up on, is the rule and which rule it follows. It's the rule number 3, because it says the sine is even, and we know that an exponent of 4 is even. So let's see what it says to do. If the sine is even, we don't save anything, but we convert what we have into that identity. And the formula sheet doesn't specify what the identity is, but I'll tell you. So we know that that particular identity is written like this. Sine squared of x is equal to 1 minus cosine of 2x. And now it looks like what's on the paper over 2. So what do we have now? We have sine to the 4th of 2x. Well, the identity still works. We just have to change things around a bit. So let's see, 1 minus cosine of 2x over 2. So first thing, we have a 2x here. The identity only works for, or the identity is originally meant to work for summing of x. So when we make this a 2x, it's almost like we're doubling every x in the problem. So 1 minus cosine, and this actually becomes a 4x, because the original identity is written for x, and now since that we have a 2x, we need to change that up. So make sure you do not forget to do that, because that's really important. And then finally, it's really important to note that this integral over here, so the 4th, this identity works for anything sine squared. So what we have to do now is square this. So sine to the 4th of 2x, which is, as you notice, exactly what we have in the integral, is literally just this. So what we're going to do now is just plug that in. So 1 minus cosine to the 4x over 2 squared dx. I know it's like a mouthful, but it's definitely what you need to do to get the answer. And don't feel, I personally I do the manipulations in my head, but don't be afraid to do this manipulation on the side if you need to kind of see how to manipulate the formulas, because in some cases it'll be an easy manipulation, but in other cases you're gonna have to square things. You're gonna have to multiply the x and make sure you make it a 4x. So I would suggest that you write it down just so you don't miss it, because it'd be so silly to get the answer wrong because of something like that. So now that we have the identity, I'm gonna erase all of this. And remember that all we're doing is following the rules on the little chart. So it's all technically there. It's just about knowing how to manipulate. So now that we've manipulated, now we have to integrate. So let's go. So the first thing I would do is just kind of factor this out and expand it essentially. So this expanded becomes 1 minus 2 cosine to the 4x plus cosine squared to the 4x all over 4. All I did was I squared the top and then I squared the bottom. And don't forget the dx. So now at this point, what I would suggest you do is remove that 1 over 4, because at least when I'm integrating, I do not like dealing with numbers inside the problem. I like to remove them from the integral and deal with them later, because it just makes things more complicated. So this, when you remove it, just becomes 1 over 4 times the integral of 1 minus 2 cosine of 4x plus cosine squared of 4x dx. Right. So now that we're at the point where it's a whole bunch of little different terms, now what I would say is you break up the integral and go one by one. So I'm gonna move the 1 over 4 all on the outside. Do not forget that 1 over 4. If you move it on the outside, remember that it goes to every single term. So I'm gonna write brackets just so that we don't forget. This becomes the integral of 1 dx minus 2 cosine 4x dx plus the integral of cosine squared of 4x dx. Do not forget a dx, because that's the proper math grammar, I would say, and you're gonna get points taken off if you don't write that. Okay, so now we just have to integrate all of those terms. And the reason why, again, I split it up is because you're gonna have to use a different rule for each one. So let's see. Erase, erase, erase. So let's go term by term. The first one, really, really easy. The integral of 1 dx is just x. So we already have that. Next term. Notice how it's cosine 4x dx. Remember, we have to look to see if the inside is on the outside. We're almost there, because the integral of, the derivative of 4x is 4 dx. All we're missing is a 4. So really, in order to get that, we just have to multiply a 4 on the inside and then divide by 4 on the outside. Because remember, what we do to the inside, we kind of have to cancel out on the outside so that we're not changing anything. So now that that's there, actually let me erase that. It's just a basic integration rule. And the integral of cosine is positive sine. So now I know that the integral of cosine 4x is sine 4x. And do not forget that little coefficient we have in the front. Oh no, sorry. Let me bring that back. Don't forget the coefficient we have in the front, which is negative 2 over 4, which is just 1/2. So so far I would say we're good to go. Now it's that last term we have to worry about. So let's go to that. So the last little term over here is the integral of cosine squared of 4x dx. I wouldn't know how to integrate that right off the top of my head, only because that is not that's not a rule, that's not an identity, but we can go back to the chart and it'll tell us what to do when we have something like this. Remember, it's still a cosine, and it's still a cosine with an even power because it's squared. So the rule from the chart will still apply. And the rule from the chart is rule number 4. It says if the cosine is even, you convert what you have to the identity. And I'll write it here. 1 plus cosine of 2x is equal to 2. Don't confuse it with the one we had just used, where it's actually sine squared of x is equal to 1 minus cosine squared of 2x. Now that we have a cosine, we're going to be using this one over here. So now let's just use it. So now I'm going to go back to the manipulations. So we have a cosine squared of 4x. Well, the identity tells us the formula for cosine squared of x. We need cosine squared of 4x. So can actually one of you tell me what the new identity is when we change the x on the inside to 4x?
Wouldn't it just be 1 plus cosine of 8x over 2?
Yep, perfect. That's it. So all we're going to do now is just plug this in over here. So this just becomes plus, I'm not going to integrate it just yet because this one needs to be changed a little bit. 1 plus cosine 8x over 2 dx. And that ends the brackets. So let me erase all of this. And now what we're going to have to do is integrate that term, which is not too bad. We just need to make sure that we're not forgetting any numbers and signs in our manipulations. Okay, so at this point, it's really up to you. You can leave it in the brackets, but I don't like to have so many things inside the brackets because then I start to get confused. So at this point, what I did in my work was I actually distributed the 1 over 4, just because we're kind of done with this part and we're done with this part. We just need to worry about this part. So I kind of wanted to get those over with and integrate the rest. So when you distribute, this becomes 1 over 4 times x minus 1/8 sine to the 4x plus 1 over 4, the integral of 1 plus cosine of 8x over 2 dx. Okay, and normally you would add a plus c, but I don't add the plus c until the last integral has been integrated. So once that you remove that integral sign, do not forget to add plus c. Let's go back. So the first thing, I noticed that there's a 1/2 in this problem. So basically what I'm going to do, let me just rewrite all of these, is remove the 1/2 over here and just bring it to the outside. So now this becomes 1/8, the integral of 1 plus cosine of 8 of x, 1 plus cosine 8 times x dx. So now we just have to integrate that. So, and it's not too bad. So again, I'm going to do what we normally do. I'm going to split it up. So this is 1/4 x minus 1 over 8 sine of 4x. This is 1 over 8 1 dx, the integral, of course. And then there's another integral we have to worry about, which is 1 over 8. Remember, the 1 over 8 goes to this one and that one. 1 over 8 times the integral of cosine of 8 of x dx. So now we just have to integrate those and then we're kind of done. So when we integrate that, we're left with 1 over 4x minus 1 over 8 sine of 4x plus, again, this is the same integral we had done before. The integral of 1 dx is just a 1 over 8x. Now it's just this one we have to worry about. But again, it's the same rule that we had been working with. All we have to do now is just make sure that the inside, the derivative of the inside is on the outside. The derivative of 8x is 8 dx, so we have to add an 8 there, and then divide by 8 on the outside, which is just 1 over 8. So this just becomes 1 over 64. And remember that the integral of cosine is sine, so this just becomes sine of 8 of x. And now is when you add the plus c, because the last integral has been integrated. At this point, this answer would be right, but one thing I would tell you guys to do is just combine like terms whenever it's possible. You'll notice that obviously the sines and the cosines can be combined because they're different functions, but notice how 1 over 4th x and 1 over 8th x are the same terms. You just have to combine them because they're really just they're really terms of x with a coefficient in the front. So when you combine 1/8 and 1/8 and 1/4, you end up getting 3/8 x minus, and then just repeat the same terms that you had before. Sine of 4x plus, this is getting messy, sorry, plus 1/64 sine of 8x plus c. And that's the answer to this problem. I know it's a little bit lengthy. That's why she's only giving us 5 problems, because like, it does require a lot of work. But the point is to get through all the work and then finally get the answer. So do you guys have any questions about this one, or
No.
no? Okay. So again, I want to try to do as many problems as possible. So let's see the next one. The next one that I have here, it's the same rules that you're used to doing, I would say. Just you have to change it around. And I'll start you guys off with this one, but I want to do like a secant problem and a cosecant problem. So for this particular one, I would rewrite it because there are no identities for like it. I always say this. I really don't, fractions are fine, but they make things a little bit more complicated. So I always like to take things out of fraction form. So this is just can be rewritten as sine squared of x cosine of x to the -1, because remember that when it's on the bottom, it's really to the -1 dx. And then at this point, now you can use the rules that are given, I would say. And for this particular problem, I actually didn't follow the rules that were there, because I noticed that for this one, it's just easier to convert a sine squared of x to 1 minus cosine of x, cosine squared of x. But once you plug that in and convert, it's actually really easy to solve. So that's how I would do that problem. And then once you do that, it's the same steps you've been doing. So let me go to the next problem, which it is a secant tangent problem. But let me see actually how many types of problems I have. Okay. All right. So I'm gonna do this one, and then that'll be it for the and then I'll do this one, number 6. And that'll be it for trigonometric integration, because I want to go into trigonometric substitution, which is the stuff with the triangle and things like that. So for this one, now we're going to move on to the secant tangent rules. So let's see what we have. It says the integral of secant to the 5th of x times tangent to the 3rd of x dx. So for this particular problem, we're going to use the same chart we've been using. Now, all we're going to do is go to the secant and tangent rules. So I'll tell you that I noticed that this particular problem actually lines up with rule number 6, which is when the tangent is odd. And basically what it tells you to do is that when the tangent is odd, all you have to do is convert, you save a secant tangent factor, and then you convert the rest to secants. So that's exactly what we're gonna do. So how do we do that? So the first thing we're gonna do, we're gonna save a secant tangent factor. So secant x tangent x. Now we have to remember that when we save this secant tangent factor, we kind of change the rest that's here. So by saving a secant tangent factor, what we have left is secant to the 4th of x and tangent squared of x dx. The next step says to convert the remaining tangents into secants, so that's exactly what we're going to do. We're not going to touch the secant tangent factor because that's what it's telling us to save. But from here, we're going to convert whatever tangents we have into secants. So let's do that. This is actually a really easy identity because the identity goes as such. It's 1 plus tangent squared of x is equal to secant squared of x. So it's really easy to manipulate in your head because tangent squared of x is simply equal to secant squared of x minus 1, which is pretty easy. All we do here is plug in this new identity. So remember, we didn't touch this, so we're leaving it as secant to the 4th of x, but we did touch this. So I'm going to plug this in, which is tangent squared of x, which is secant squared of x minus 1 dx. Oh, sorry. Let me erase this. So now we've done what the rule says. We've saved the secant tangent factor, and we've converted every other part of the problem into secants. So let's expand, or let's distribute this part first, and then I'm going to distribute this part to every single term, just like we've been doing. Then we're going to break apart the integral and then do all the rules that we've been doing. So secant of x, tangent of x. When you distribute this, this becomes secant to the 6 of x minus secant to the 4th of x dx. At this point now is when I would tell you to distribute and do the separate integrals. So this is secant to the 6th of x times secant tangent of x. Remember, you want to make sure that your term with the exponent, the derivative of the inside has to be on the outside. That's always your goal, at least for the majority of this trigonometric integration problems. Notice how the derivative of secant of x, if you remember from AP Cal AB, is secant tangent. So it's very, very easy. It works out really nicely. Minus secant of x to the 4th, and then a secant tangent x dx. And now all we have to do is integrate. So let me erase everything on the top and integrate. So remember, what we're always looking for is to see if the derivative of the inside is on the outside. I'm going to keep repeating it. In this particular problem, it works out beautifully because the derivative of the inside is secant tangent dx, which is, it requires no manipulation, no minus, no fraction, no numbers. It's perfect. So all we have to do is take the secant that we have, add an exponent, divide by that number, move on to the next one, which is the same exact rule. We add an exponent, divide by that number, don't forget plus c. And then the final answer for this problem, converting things and making it prettier, is 1/7 secant to the 7th of x minus 1/5 secant of x to the 5th plus c. And that's the answer to this problem. Did that one make sense, or did I lose you guys at some point?
No, it makes sense.
All right, perfect. All right, so now we're gonna do one last trigonometric problem, and basically what we're gonna do is we're gonna be manipulating this cosecants and tangents. Remember what I told you in the beginning. Sine and cosine will go together. Secant and tangent will usually go together. And then cosecant and cotangent will usually go together. Notice how in this problem, it's cosecant but tangent. So when I first saw this, I was like, these two usually don't go together. So it's gonna require some form of manipulation. So going to that rule, I'll tell you guys what I first did when I saw this. So let me erase this. Okay, so we have cosecant to the 4th of 3 theta times tangent to the 4th of 3 theta d theta. So with this particular integral, the first thing I did was I tried to cancel things out, because since we don't have the correct pairing, since it doesn't go in the right pairing, I noticed that in order to kind of work this out, we're probably gonna have to cancel things out because there's no pairing that goes with cosecant and tangent. So what I did was I made this cosecant into a 1/sine the 4th 3 theta, because in case you remember, cosecant to the 4th of 3 theta, a lot of this is just remembering the identities, is equal to 1/sine to the 4th of 3 theta. It's really 1/sine. So that's the first term. The second term is really sine over cosine, if you remember correctly. Because remember, tangent is always equal to sine over cosine. But tangent of 4 to the 3 theta is equal to sine of 4 to the 3 theta over cosine of 3 theta to the 4th. So that's exactly what I wrote. And if you notice, it actually works out really, really nicely because you'll see that this denominator cancels out with that numerator and it works out perfectly. So that's why I really liked the method I chose, because all you have to do is expand, I guess, rewrite is another word to say that, and then just cancel out. And now all we're left with is a 1 over cosine to the 3 theta. So at this point, now all we have, again, like I said, is 1 over cosine of 3 theta to the 4th d theta, which conveniently can be written as secant to the 4th of 3 theta, because as the identity goes, 1 over cosine to the 4th of 3 theta is equal to secant to the 4th of 3 theta. A lot of these identities are just kind of doing like the reciprocal. So 1 over cosine is equal to secant. 1 over sine is equal to cosecant. 1 over tangent is equal to cotangent. So you'll notice that, at least with the identities. All right. So let's see what we can do now. So now that we've essentially gotten rid of the odd pairing in this problem, now all I have to do is integrate as we normally would. So we have secant to the 4th of 3 theta d theta. So what's secant to the 4th of 3 theta d theta? I'm gonna go back to the chart and see what to do when we have a secant to the 4th with an even power. And basically, what it tells you to do is to save 1 secant squared and then convert the rest to tangent squared. It's always the same rules. It's always the same chart. We just need to manipulate it so that we can get to the right problem stem, I would say. So I'm going to do exactly what it says. It's rule number 5. When the secant is even, you save 1 secant squared. So we're going to save 1 secant squared of 3 theta. And then we're going to convert the rest to tangents. So let me erase this. The identity goes as such. We had kind of gone over this in the previous problem, but the identity is 1 plus tangent squared of theta is equal to secant squared of theta, and that works with this even with a different number. So 1 plus tangent squared of 3 theta is equal to secant squared of 3 theta. So secant squared of 3 theta is equal to 1 plus tangent squared of 3 theta. So remember this, to save the secant squared factor it told us to do, and then to convert the rest to tangents. So that's what we have. Now all we're going to do is distribute, integrate, and hope for the best. So let me erase this and continue to integrate. So at this point now, when we distribute this, we have secant squared of 3 theta d theta plus a tangent squared of 3 theta. I'm going to rewrite this like that, times secant squared of 3 theta times d theta. Kind of ran out of space there, but you guys get the point. So now all we have to do is integrate. So you'll notice that this first term over here is a formula we already know. So secant squared, the integral of secant squared is tangent. But remember, the inside has to be on the outside too. So in order to kind of get that and balance it out, we have to add a 3 here and a 1/3 on the outside. So this just becomes 1/3 tangent of 3 theta. And that's just a formula from AP Calculus AB. Next one. The inside has to be on the outside. The derivative of tangent of 3 theta is secant squared of 3 theta times 3 d theta. Notice all we're missing is a 3, so there, we have to add the 3 there, a 1/3 over here. So now that we've done that, we can use the power rule. So with that, don't forget the 1/3 we added, but it's tangent of 3 theta to the 3 over 3. Now that we've done the last integral, don't forget plus c. So at this point, now all we have to do is, I would say, rewrite it just so it looks prettier. So for this last step, it's 1/3 tangent of 3 theta plus 1/9 tangent of 3 theta cubed. Oh no, I wrote that wrong. Sorry. Plus c. And that's the answer to this problem. So again, I know it's a lot of steps, it's a lot of manipulation, it's a lot of work, but that's why we have 5 problems for this quiz, and that's why it's just important to know the chart and know what to do, because once you do it, it actually doesn't end up being that hard, because what you'll always notice is that the inside will be very, very close to the outside, and you just have to do a slight manipulation to get there. And that's the whole point of these rules. So I think we've done quite a few trigonometric integration problems, but now we're going to move on to trigonometric substitution, which involves the triangle and things like that. So on this particular review, I actually put quite a few practice problems for these problem sets. I'm trying to look to see which ones are the best to do. Okay, so going back to the second little chart that we had gone over in the beginning of this video, remember the formulas. So when you have something like this, a squared minus u squared, that gives you permission to write u is equal to a sine of theta. When you have and that actually applies to this problem. Remember, a is like a number, u is like a bigger number, like it has something added to it. So there's like an x, there's a cosine, there's a sine. In these problems, it's always going to be an x. Your a will be like a constant, it'll be like 1. Your u will be like an x or something like that. That's the first formula. And I put different practice problems for each type. The next one, let me see where I can find the first one like that. Here. When you have something like a squared plus u squared, that gives you permission to say that u is equal to a tangent of theta. And the difference between the previous one is that now there's a plus. So for this particular problem, notice how there's a plus there. In this problem, a would be 3, u would be x, and then we would know that x is equal to 3 tangent of theta. But that's just the first parts of this problem. Let's go and find the last example, just so you guys know what I'm talking about. And it's right here. So the last problem, I guess, with the trigonometric substitution involves u squared minus a squared. And this gives you permission to say that u is equal to a secant of theta. The difference between this one and the previous ones is that now the u and the a are flipped. So just keep an eye out for that. And I'm actually going to try to do one of each. No, I am going to do one of each. This review actually has a multiple of each. And then I want to do one of each, and then I want to do the last two because they're very interesting. So let's do one of each for these. And I'm going to do the hardest one first for each problem, just so that helps you guys out. So this one I would say is probably the hardest one for the sine issue. Remember that we know it's a sine problem, a sine conversion, because it's 4 minus x squared, which is a minus u squared, which is a squared minus u squared, which is the first little formula. So let's set it up at first. So for this particular problem, it says the integral of dx 4 minus x squared to the 3/2. The first thing you might be wondering is, hey, there's no radical. What do we do? Because in every other problem you see, it's usually like 1 over radical 4 minus x squared. Well, what I would suggest you do is just convert this to a radical, which it can be done, because this 3/2 exponent, it's really saying 3 times to the 1/2. And you guys should know that any exponent to the 1/2 is a radical. So it's like we're almost there. We just have to manipulate it. So how do we do this? Well, remember that when you have, this is the easiest way to change it around. This can just be rewritten as 4 minus x squared to the 1/2. Sorry, I wrote it as 1/3. All times 3. And notice that when you have two sets of parentheses with exponents, you can just multiply those exponents you get the same thing, which is exactly what we have here. So that's why we have permission to do that. So now all we have to do is just kind of rewrite this. So essentially what you have now, and not forget the dx, is 4 minus x squared, all in radical, cubed dx. So now it's the same problem, we just changed it around just so that it looks like the formula that we're given. So the first thing that you have to do when you have this, figure out what your a and your u are. The whole point of trigonometric substitution is to substitute every single thing in your problem and make it something with trigonometry. So let's do that. Remember, I always like to add let, just because it's not given in the problem that a is equal to this. We're letting a equal this. So for this problem, we're going to let a equal 2, because remember, the formula is a squared minus u squared. So a is just 2, because a squared is 4, so a has to be 2. We're going to let u equal x, because u squared is x, u has to be x. Now, and remember the formula, it says that if that's true, then u is equal to a sine of theta. So now, based on this info, we know that x, which is u, is equal to 2 times sine of theta. And that's the first, I would say, important part of this problem. Now, what we're going to do is kind of just fill in the missing spots. So notice how this problem has a dx and an x squared. So x squared is just 4 sine squared of theta, right? All I did was square this. Dx, well, let's just take the derivative of x. The derivative of 2 sine of theta is 2 cosine of theta d theta. It's that simple. And then finally, what we're going to do now is we're going to figure out the radical part, because the whole point of this is to plug every sine or cosine or whatever into the original problem to make it easier to solve. So our little radical for this problem, where should I write it? I guess I'll write it over here in this tiny spot. I'll write it in yellow. Ooh, sorry. I don't know why it's doing that. Okay. Whatever. 4 minus x squared. I'm actually going to erase this over here and do it over here so that there's some more space. So we're dealing with, I don't know why it's writing in blue. I wanted it to write in yellow. Okay, good. 4 minus x squared. We know that we just said that x squared was 4 sine squared of theta. So now all we have to do is just convert this into an identity. And that's how we'll figure out what this radical is equal to. So the first thing I do is I usually just move the 4 on the outside, because then it starts to look more like an identity we know. So by doing that, it's the same number. We know that since we're multiplying them, we can split them apart. So 1 minus sine squared of theta. The square root of 4 is just 2, so we have that. And the identity, we've kind of gone over this identity before, but 1 minus sine squared of theta is equal to cosine squared of theta. So we know that everything in the radical is equal to cosine of theta. So now that we have all those parts labeled, now it's just about plugging things in. So now is when we plug things into the original problem. So I would say keep this, have these parts labeled, because I'm going to erase the whole screen just because it's a little messy and I want to start from scratch. So let's go to our original problem. The original problem goes as such. It's 1 minus 4 minus x. Sorry, it's 1 over radical 4 minus x squared cubed dx. Let's plug in what we know. We just said that the radical, remember all the solving and all the manipulation, we just established that the radical was equal to 2 cosine of theta. So this radical, I'm going to plug in a 2 cosine of theta. Remember that it's cubed. All we have left is the dx. We had already established that dx was equal to 2 cosine of theta d theta. Now we've plugged everything in, and now we can integrate using trigonometric integration, which actually goes back to our first few problems that we did. So let's just see what we can cancel out first. This over here is 2 cosine of theta cubed, which is 2 cosine of theta 3 times. So I'm going to save one, and so I'm going to make this 4 cosine squared of theta, 2 cosine of theta, d theta, because I want to cancel these out. And that's exactly what I just did. So now at this point, all you're left with is 1 over 4 cosine squared of theta, d theta. Let me erase the top and continue solving. Remember, I like to remove any coefficients and put them in the front of the integral. So this just becomes 1 over 4 times 1 over cosine squared of theta, d theta. This can just be converted to secant squared of d theta. And as you all know, secant squared, the integral of secant squared is a very, very popular formula from AP Cal AB, which is just 1 over 4 tangent of theta plus c. So now we appear to have our answer, but remember, this is not our answer. And this is where the triangle part comes in, because notice how our answer is in x, and we have everything in theta right now. So we're not done yet, because theta was like our little trick to get the answer, but now we have to put things in terms of x. So let's go back to right triangle trigonometry from geometry honors. Earlier on, we said that x is equal to 2 sine of theta, right? That means that sine of theta is equal to x over 2. Let's go to triangle trigonometry. If you guys remember SOHCAHTOA, let's look at sine. We know that opposite over hypotenuse is sine. So that means opposite over hypotenuse is sine. So if theta is, let's say, just this angle over here, we know that the opposite, which is the opposite, over the hypotenuse, remember the hypotenuse is that longest side, is sine. So we already know 2 parts of the triangle. All we have to do is figure out the last part. And the reason why we're doing this is because we need to find tangent of theta. And in order to find tangent of theta, we need to do opposite over adjacent, which is this missing side over, sorry, no, I said that wrong. It's this side over this missing side. So we're almost there. We just need to figure out what that missing side is. Now I'm going to go back to another geometry honors concept, which is Pythagorean theorem. We know that when we have a right triangle, we know that one side squared plus another side squared is equal to this side squared. So x squared plus question mark squared is equal to 2 squared, which is 4. So this missing side is essentially question mark squared 4 minus x squared. And when we square root this, we get that that missing side is equal to 4 minus x squared. And a little trick Miss Q taught us. You'll notice that whatever you get as the missing side should equal to what you have over here. Notice how it's the same thing. It's the same radical 4 minus x squared. We got that. So we're on the right track. And that'll kind of tell you if you're doing the right thing or not. So let's see. We now know that the missing side is 4 minus x squared. That you can just do in your head. But I just wrote out the Pythagorean theorem just for you guys to see it. And now we can figure out what tangent of theta is. Tangent of theta, remember, tangent is opposite over adjacent. So opposite is x, adjacent is 4 minus x squared. So 1 over 4, opposite over adjacent, x over 4 minus x squared plus c. And I guess the proper way to write this final answer is just x over 4 times 4 minus x squared plus c. And that's the answer to this problem. Does anyone have any questions about what we did?
No.
You got it?
Yeah.
All right. So I'm gonna move on to the next type of problem and go through it just a little bit quicker. And then what I'll do is the multiple choice problem, and then that'll be it. Okay. So next problem. We're gonna do another type of trigonometric problem, which is, I'll do number 11. Actually, let's do number 12. That one's a little bit harder. So for this problem, actually, no, let's do number 11 here, because this one actually requires a different rule. So I don't want to go into that right now. But for this particular problem, we're just going to be doing the exact same thing. And it's actually written a little bit nicer, so we don't have to do any first-hand manipulation. Remember, we're going to let a equal 3. We're going to let u equal x. This gives us permission to say that x is equal to 3 tangent of theta, because now there's a plus. What do we do first? Let's figure out what x squared is. X squared is 9 tangent squared of theta. There's a dx, so let's figure out what that is. Dx is 3 secant squared of theta d theta. And let's do the radical. So the radical is 9 plus x squared. We know that x squared is 9 plus 9 tangent of theta squared. This just becomes 9, radical 9 times 1 plus tangent squared of theta. This becomes 3. And if you remember the identity, 1 plus tangent squared of theta is equal to secant squared of theta. So this we can just become secant squared of theta. And this is now just secant of theta. So everything in the radical is 3 secant of theta. So now that we have all that stuff identified, all we have to do is plug in. So let's just do that. The radical we just solved, we plug it in at the bottom, is 1 over, we're going to plug it in, is 3 secant of theta. Now we just need to figure out what dx is. Dx is 3 secant squared of d theta. So it's just that. Notice how this cancels out with this. All we're left with is a secant over here, because there's 2 on the top and 1 on the bottom. So now all we're left with, and I'm going to clear this out, is a secant theta, essentially. So now it's just about knowing the formula. So going back to our AP Cal AB integration formula sheet, we know that the integral of secant of theta is ln of the absolute value of secant of theta plus tangent of theta, of course, plus c. So this one is actually not too bad. All you have to do is just figure out what secant of theta is and what tangent of theta is. But notice how, let's go back to what we did in the beginning. Now we're going to do the triangle again. From the beginning, we knew that x is equal to 3 tangent of theta. This means that tangent of theta is equal to x over 3. So we already have one done. We already have this one done. We just need to figure out what secant of theta is. So going back to SOHCAHTOA, let's plug in the right values of the triangle. So remember, tangent of theta is opposite over adjacent. So this is x and this is 3. The missing Pythagorean Theorem part is just x squared plus 9. Because it's one side squared plus another side squared, all in the square root. So finally, we just need to figure out what secant of theta is. There's 2 ways you can do it. The way I do it is I just know that secant is the oh my god, I forgot the word. It's the flip of it's the reciprocal of cosine. So really, when you're doing, let's say that cosine is opposite over hypotenuse, adjacent over hypotenuse. Secant of theta would just be hypotenuse over adjacent, because it's the reciprocal. Remember, the reciprocal is just the flip. So when you do that, since we're looking for secant, all we have to do now is do hypotenuse over adjacent. So secant of theta is equal to radical x squared plus 9 over 3. And that's how we solve it. You could always just face, if you ever forget that rule, you can know that secant of theta is equal to 1 over cosine of theta. And we know that 1 over cosine of theta is adjacent over hypotenuse, which is 3 over this, x squared plus 9. And then when you simplify it, you get the same thing. That's just a backup, but I think that's an easier way to picture it. So now that we know what secant of theta is and what tangent of theta is, we just have to plug in, and then that's our answer. So let me erase so there's space for me to write the answer. I'm going to save those two values just so we have them. And now all we have to do left is write ln of secant of theta plus tangent of theta. Which is radical x squared plus 9 plus x all over 3. I didn't write each one individually because since they have the same denominator, you can just write the numerators. And then that's the answer. Does that all make sense?
Yeah.
Or did I lose you? It's good?
No, it makes sense. Yeah.
Okay. So last type of problem. We're gonna do the secant one now, which is number 13. So practice with secants. So for this particular problem, now we're just dealing with the rule for secants. So let's start again. We're gonna let u equal x. Remember, it's the same radical, it's the same thing. We're just changing things around. We're gonna let a equal 1. We're gonna let x equal to 1 times secant of theta, which is just secant of theta. Let's just figure out some things first. X squared is secant squared of theta. I see that there's an x cubed in the problem, so I'm actually going to figure out what that is too. X cubed is just secant cubed of theta. We have a dx, so let's figure out dx. Dx is secant tangent d theta. And then the last but not least, we have to deal with the little radical. So we have x squared minus 1. We know that x squared is secant squared minus 1. And that's the exact identity that we did. 1 plus tangent squared of theta is equal to secant squared of theta. We subtract 1 from both sides. This just becomes equal to tangent. So this is just tangent squared of theta. And we know that the radical is now equal to tangent. That's simple. So now we're going to plug in. So when we plug in, just keep clearing. Okay, I'm gonna do it in green so it's easier to see. When we plug in, we're just gonna plug in our givens from the side and see what we can cancel out. So x cubed is secant cubed of theta. The radical we just figured out was tangent of theta. And then last but not least, we have the dx, which is secant tangent d theta. This cancels out. We're left with secant to the 4th of theta d theta. And now all we have to do is integrate that. And then of course, use a little triangle and figure out and replace every theta with an actual x. So let's go there. I'm gonna erase everything not in green just because we're kind of done with that at this point. So notice how the secant to the 4th isn't a formula in our AP Calculus integration formula sheet. So we're gonna have to go back to our little chart and tell us what to do when we have an even secant power, which is rule number 5. When we have an even secant power, we say 1 secant squared, and then we convert the rest to tangents. Just from memory, I already know that secant squared is equal to 1 plus tangent squared of theta. That's the formula. And now all we're going to do is distribute, integrate, do everything that we've been doing. When you distribute this, we're left with secant squared of d theta plus, I'm going to put the tangent in parentheses, and then the secant on the outside. When you do this, this is now our AP Calculus formula problem. This integral of secant squared is simply tangent. The integral of this, remember we're checking to see if the inside is on the outside, derivative of the inside is on the outside. The derivative of tangent of theta is secant squared of theta, so it works perfectly. Now you can use the power rule and integrate as such. So this just becomes tangent of theta to the cubed over 3, all plus c, of course. So we're almost done. Now we just need to figure out what tangent of theta is. So let's go back to our little triangle. I'll do it really small on the bottom. The triangle, that came out bad. The triangle. Okay, so from the beginning, we have x is equal to secant of theta, which means that secant of theta is really equal to x over 1. Going back to SOHCAHTOA, remember secant goes with tangent, so secant is really hypotenuse over adjacent. So hypotenuse over adjacent, x over 1. We're just missing that last side, which is x squared minus 1, according to Pythagorean theorem. Now all we're missing is tangent, because that's what the problem is asking for. And I know that tangent of theta is opposite over adjacent, which is x squared minus 1 over 1, which means that tangent of theta is simply the square root of x squared minus 1. So now all we have to do is plug that in to our little problem, and then we have the answer. So let me erase all this again and write the final answer at the top. And I'll kind of show you what she did to kind of simplify it. So tangent of theta is equal to radical x squared minus 1. So all you have to do is plug in this right here, next term. This is really a 1/3, and this is all cubed, but this can be rewritten so that it looks better, I guess, plus c. Remember that this is technically to the 1/2, so the way she wrote it was she actually distributed the 1/2 and 3. So this is still the same number, plus 1/3, and she just wrote this as x squared minus 1 to the 3 over 2, because you can multiply the exponents and get the same answer. And that's the answer to this problem. So that's the last of the 3 different types of trigonometric substitution problems. And yeah, so they're not too bad as long as you know what to do and all the secant tangent rules and things like that. So finally, I'm going to do one last problem with what you would do if you have a definite integral, which is when it has bounds, where it's like from 1 to 2, things like that. And that's the multiple choice question from this little review. So let's go to it. And all I'm going to do is just tell you how to change it around, because this particular problem is saying what are the new bounds when you change it to thetas. Because when, let's say that this integral over here, let's say that we made this into sine of theta, just based on all the little manipulations we did. Well, we changed the variable. We're now dealing with theta. We're not dealing with x's. And the bounds from 0 to 1 are when we're dealing with x's. So it's important to remember that when we're not dealing with x's, when we're changing it to theta, our bounds have to change too. So that's the most important idea behind this type of problem, I would say. So let's just start it off the way we normally started. Notice how this problem isn't even asking us to solve it. It's just asking us to write the new integral with the new bounds. So, Natalie, which type of, would it be sine, tangent, or secant based on what you see over here, based on the formula?
For which one?
For number 15.
Oh, okay. It would be 1 minus, so it would be the sine, a sine of.
Yeah, it said it in the problem, so I crossed it out, but yeah, it is the sine one. So, how about you tell me what, like, a lot of this stuff is? So, what's a going to be equal to?
A would be just 1.
And what's u equal to?
U would be equal to sine of
Wait,
theta.
not yet. Remember, we do a and u first. A is 1, u is going to be x, remember?
Okay.
Now, we use the rule that says u is equal to a sine of theta. We're going to plug in what we have here, and that's how we plug it in, I guess. I did that wrong. This goes here, that goes there. This just becomes x sine of theta. Does that make sense, right?
Yeah.
Like, you know to plug it in?
Mm-hmm.
Okay. So at this point now, it's just doing what we've been doing. We figure out what the x squared is. That's just sine squared of theta. We figure out what dx is. That's just cosine of theta, d theta. And then the radical. So what would the radical be equal to, Natalie? Like plug it in for me.
You just did it, the 1 minus x squared.
Okay, but what do we plug in for x squared?
Oh, for x squared, we would plug in sine squared of theta.
And what's 1 minus sine squared of theta? It's an identity, remember?
Cosine squared of theta?
Yes. And what's the square root of cosine squared of theta? Yeah. So now all you have to do is just kind of see which one. Well, now we've kind of dealt with the inside, but we haven't done the bounds yet. Okay, so I'm going to show you guys how to do the bounds. So actually what I'll do first is plug it in. So let me do the bounds first, actually. Okay, so our original bounds, the lower bound is 0, and the upper bound is 1, right?
Yeah.
All right, so, and that's when we're dealing with x's, but we're dealing with theta in this particular problem. So let's use this little thing over here and tell us what theta is. We're going to use this part of the problem, x is equal to sine of theta, to tell us what it's equal to. So when x is equal to 0, sine of theta will have a certain value, and when x is equal to 1, sine of theta will have a certain value. Now this is just knowing the unit circle. So I don't know if you remember it, because I know you told me you don't have it fully memorized. Do you want to take a guess of when sine of theta is equal to 0?
Sine would be equal to 0 when
Like when
it's
it's what?
2 pi or pi, right?
What?
When it's either 2 pi or pi.
Well, sine of the what's 2 pi? 2 pi is right, but usually we go with like the smallest value. 2 pi is right, but remember 2 pi is when you make a full 360.
Mm-hmm.
So what, can't you just say you're starting at 0?
Oh yeah.
And then when is sine of theta equal to 1?
That would be when it's pi over 2.
Yeah, that's it. So those are our new bounds. We started with 0 and 1. Our new bounds are 0 and pi over 2. So we really only changed 1. So now we're going to take all this like information that we have here and make it an integral, and then that's our answer. What can I erase? Okay, I'm going to erase actually this, because this is like the most irrelevant. And I'm going to put like a little box around the stuff that we're plugging in. Okay, so we have the integral of 0 to 1 minus x squared dx. Let's plug in. First, let's plug in our bounds. So our new bounds are 0 and pi over 2, right? Our radical we solved, and you told me it was cosine of theta. And lastly, our dx we solved, and we figured out was cosine of theta d theta. So this integral is really the integral from 0 to pi over 2 cosine squared of d theta. And that's the answer to this problem. You'll notice that it's choice B, right? This one. So yeah, you don't have to solve it. You just have to figure out what the integral is. I guess in a normal problem, you would do the triangle and all of that, but for this problem, you don't have to do that. So don't worry. So that's all that I have time to do today. But you know that if you have any questions, you can just text me. And yeah, so I'm gonna end the session, and that's it for today.
Bye. Thank you.